Hello everyone, welcome back to one more question on organic chemistry. This is about the synthesis of vanillin, which is the molecule behind vanilla flavor, and all of you know that how important that flavor is, and most of us have loved this flavor in different food products, maybe ice cream or something else. Let us go to the question. This question was about the synthesis of vanillin, how it can be synthesized. They have been given four options. In option number 1 and option number 3, that is A and C, they are asking about if we have taken 1,3-dihydroxybenzaldehyde. That means if this methyl group is not methyl, if this is hydrogen. And then this is being treated with 1 equivalent of sodium hydroxide followed by reaction with methyl bromide. What is going to happen? So we'll be seeing when 1 equivalent of sodium hydroxide is being reacted, which of these two OH groups would be protonated if we are starting from dihydroxybenzaldehyde. Also, in option number D, they have, rather than using same molecule that's starting from 1,3-dihydroxybenzaldehyde, now rather than using one equivalent, they are using two equivalents of sodium hydroxide, and then again they'll be using one equivalent of methyl bromide. So here again they want us to know which oxygen, meta 1 or the para 1, is being deprotonated and subsequently being reacted with methyl bromide in the SN2 fashion, which would be like Williamson ether synthesis. So we'll be this going to the D option is going to be a rather interesting case. We'll be seeing that in a moment. Also in option number B, they have talked about reaction of the 1,2-methoxyphenol with the chloroform in presence of aqueous KOH. This is looking like a Reimer-Tiemann reaction. We have been seeing that reaction. We can be seeing the product, how that formylation at the ortho and para position of which can be possibly taking place. So we'll be going deeper into all these options one by one, and then we'll be coming to the conclusion. We'll be seeing what the final answer is going to be. So the first option, and of course the third option as well, put together, we can say. Here what we have been told that we are starting with this compound where both the positions are basically OH. So we have written 3,4-dihydroxybenzaldehyde we have taken. First step, sodium hydroxide, 1 equivalent, that's going to be acid-base reaction because this phenol is acidic, this is basic. So we'll be getting, because there's only one equivalent being used. So what we expect only this OH being protonated because this oxygen is more acidic. The reason for saying that is because when the CHO group is exerting its minus M effect, we are getting delta positive charges onto ortho and para positions. So when this carbon is having more positive charge, this OH is going to be relatively more acidic in comparison to the other one. Right? So if this hydrogen is more acidic, during deprotonation, we expect that this hydrogen will be going and we are getting O- ion being generated. Now the second step is reaction with methyl bromide 1 equivalent. So the second step is going to be basically SN2 reaction of PHO minus, that is phenoxide, and this is going to be on methyl bromide. So we can write over here methyl bromide, that is your CH3Br. So we understand this is going to be one SN2 attack, and this reaction is basically like the second step is basically the Williamson ether synthesis, where phenoxide ion will be attacking onto alkyl halide in SN2 fashion. This is going to be the backside attack. Br leaves, and we will be getting methylation onto the para position. That is going to be our final product of this reaction. And the product which we have not formed, we have formed now. Option number A and C are governing that. This product is not the vanillin. This is something else. This is basically the isomer of the vanillin, and in particular this is the position isomer of vanillin. That is the thing. This compound is not vanillin. This is the position isomer of vanillin, where the positions of OH and methoxy have been swapped in comparison to vanillin molecule. Okay, going to the second option. This option was about the reaction with the CHCl3, that's chloroform and KOH. We know that when we are reacting these two compounds, we are getting some dichlorocarbene generated, and dichlorocarbene is going to be having its nature as electrophilic. So because this is electrophilic in nature, what we expect, this will be doing that electrophilic aromatic substitution. We call this as Reimer-Tiemann, which is basically SE reaction, substitution electrophile, because electrophile being generated is going to substitute the hydrogen. And we know from our reaction mechanism that the orthohydrogen or parahydrogen, both of these can be substituted in this Reimer-Tiemann kind of reaction. And also we understand this ortho product with respect to OH group is going to be the major attack in this reaction, as we have been seeing in the Reimer-Tiemann reaction all the time. So when ortho attack is being favored with OH, this compound is going to be the major product. And in fact, in the question, they did not ask as the major. They had asked that P can be obtained as one of the product. So this is also going to be like we are definitely getting this compound being formed. The vanillin, this one is going to be the minor product, but this is definitely being formed as one of the product, and one of this isomer we are getting generated as the major one. Doesn't matter, this qualifies to the correct option. We are going ahead with this option. And in fact, here the attack of the dichlorocarbene when it was happening. So when this compound is, I'm writing from the ortho attack, which is the major one. So when dichlorocarbene is attacking onto this compound, we are getting something, some intermediate, which because this is O minus, this is going to be more electron rich resin because of its plus whatever electron density over here we are having. That's why the ortho product is actually being favored in this Reimer-Tiemann reactions. So this being electron rich resin, this double bond is being attacked onto the dichlorocarbene. So if we should have written it, possibly not there, we should have written it here. So when that bond is being this bond is actually attacking the dichlorocarbene Cl2, then we'll be getting some structure which looks like this is double bond O, there is a hydrogen, and there is a C having two chlorines present like this, but this chlorine gets a negative charge, and then OMe here we have, then we are having the intramolecular proton transfer, in which the hydrogen from the ortho position, this hydrogen is actually getting transferred onto the CH itself. This was the product being formed. This is double bond O, this is OMe itself. And now this is going to be a case of tautomerization, where this hydrogen will be going on to this oxygen, and we can be then seeing this hydrogen which was present here. Basically this undergoes tautomerization, we can be getting phenolic compound being formed, and at the same time hydrolysis is taking place. So the two OH present on the same carbon, that geminal dihalide, will be undergoing hydrolysis, and that is going to produce the aldehyde group in the subsequent step. So this is converting into OH. Actually that OH being generated, because reaction medium is basic, is going to give us phenoxy group. We are writing here because reaction medium was basic, we are getting this as the final product. And final product after acidification, of course, could be coming this and this, the second one being the major one, right? Okay, moving on. This was the option number 4, which was, we said, is going to be quite interesting case. The reason being, we have got now two equivalent of OH. So both the OH are getting deprotonated in the first step, and now our thought is more electron rich oxygen is going to be better nucleophilic in nature. So we are going to see the electron density. This is the basically compound what is being formed. We are going to see the electron density, and we are realizing that our meta is going to be relatively more electron rich, because para position is going to have -m effect, as we have written earlier. Because this is -m, this is having delta positive charge, this is having delta positive charge, this oxygen is less electron rich. So the other oxygen which is present at meta position is going to be more electron rich. So now again we are having Williamson ether synthesis of more nucleophilic oxygen which is at meta position. This is going to attack onto this methyl bromide, and we are going to get this thing as the major product. This is going to give us vanillin in the major yield, because the other thing, the para OH which was converting into paraphenoxy thing, that is not a good nucleophile, that will not be giving you the minor product. This is giving you the vanillin as the Maser product, right? Looking back at the questions, the options what we had, now we can revisit that question and we can see which was right, which was wrong. Yeah, so first one was not right because this did not give us vanillin, this gave us its isomer. So isomer was formed, that means C was correct, A was not correct. B, we have seen this was obtained as one of the product. It was not major, it was minor one, but this was definitely one of the product. That's true answer. And option number D, they said when 3,4-dihydroxybenzylate, that 2 equivalent of sodium hydroxide we talked about, this is again going to give us vanillin. So the correct answer to this question was supposed to be B, C, and D. Okay, interesting question. And that's actually all about the question. We have answer as B, C, D. Some more information coming in about the vanillin. Just have a look. I will not be talking about all those things. That is just a slide, so you can just have a look. That's all for now in this question. Thank you. Bye bye. See you next time.